All right. Hello again. This is week 2, lecture 1, second part of this lecture of week 2. We're going to be talking about Newton's third law of motion. Now, Newton's third law of motion is a little more subtle, if one might argue, than the first two laws. It's subtle in the sense that it involves forces in pairs. When you think of the third law, you always have to realize that forces are in pairs. So what does that mean? It means that if you think of one object exerting a force on a second object, it also means that the second object exerts a force on the first. This force is of equal magnitude, the same size, but it's in the opposite direction. And so it is directed directly against the force due to the first object. This is known as action equals reaction. The action of one object onto another is equal to the reaction of that other onto the first object. So if an object A causes a force on an object B, then the object B exerts an equal force in the opposite direction on equal A. Why is that, might you ask? It is the result of inertia. If it takes a force to put an object in motion, it means the object is resisting acceleration. And this resistance is proportional to its mass, to its inertia. And so that means if I apply a force onto an object, this object is resisting acceleration. That means it is exerting a force onto me, who is trying to push it. So effectively, we can write it down as the magnitude of the forces of B on A is equal to the magnitude of A on B, B and A being the two objects at play. What is not written here is that the directions are along the same line, but in opposite direction. So let's consider a couple of examples of this. If you are, for whatever reason, pushing against a wall with your hands, you might be straining. Maybe you're doing stand-up push-ups, some kind. You're pushing against the wall with your hands. And you can feel how much of a force you're exerting by the tension in your muscles. But the wall being anchored into the floor and the building in general, it's not moving. And you're not moving. But there's this tension in your muscle, right? And so what's going on here is that you're applying a push on the wall, and effectively the wall is pushing you back. And so you're trying to move the wall, and the wall is resisting your push. And everything that happens in nature, in the universe, is working this way. For every action, there's always a reaction, a force exerted by the other object backward. It's the case, for instance, when you pull a drawer out of your dresser. You pull on the drawer, but oftentimes you will feel that there's a bit of resistance, right? And so to pull on the drawer, you need to exert some tension in your muscle, some force. And that means that the drawer itself is resisting the motion of being open. Sometimes drawers could be stuck, and then you really have to exert a force, a strong force, to pull them out. So the force acting on the drawer is counteracted or action-reaction by the drawer on your hand. This takes many facets. Imagine a book on a table. Imagine a book on your desk. This book, let's pretend, has a weight of 5 Newton, as illustrated here. If there was no desk, if you were able to take the book, remove the desk, what would happen? The book would fall until it reaches the ground. And so there's a force being acted on the book by the presence of the earth, right? The earth is pulling on the book with a force of 5 Newton. But obviously the book is standing or sitting on the desk. It's not moving. And so the book is not moving. So that means there is an equal force from gravity and the desk itself. The desk is pushing on the book upward with a force equal to the weight of the book. In turn, that means that the book is exerting a force on the desk. The book is pulled by gravity, and as such, it wants to fall down. It wants to accelerate down. But the desk is there, and so that means the book is putting pressure on the desk downward. And so the action of the book is to exert a force on the desk. The reaction of the desk is to exert a force on the book. So gravity is out of the loop here, so to speak. What's happening is the book pushes on the desk, and the desk pushes on the book. Action equals reaction. Now imagine that you replace the book by something very heavy. Very, very heavy. Bricks of lead. Many bricks of lead. It stands to reason that at some point, the desk will not be able to sustain the weight of the bricks, and it will just collapse. It will just break apart, right? And so at that point, the desk will fail to provide the force to maintain the bricks at rest, and the bricks will fall under the action of the pull of gravity. And so this would be a case where suddenly the force imparted by the bricks onto the desk no longer have sufficient reaction or sufficient compensation, if you will, to be maintained at rest, and they will just fall through the desk and destroy the desk in the process. The same thing happens to us humans, or everything else on the surface of the earth, as we stand on earth. The earth is pulling us down, right? And so if there was no surface, we would just fall through. In fact, if you were on the top of a building and you were just to walk off the top of the building, please don't do that. Don't do this at home. Obviously, you would be falling down. So if you're at the top of a building, gravity is pulling you down, but the building is exerting a reaction force that keeps you at the top of the building. Remove the building. Let's do this straight on the surface of the earth. Earth is pulling you down. The ground is keeping you up, right? So what's going on here? The earth is exerting a force on you, but you are also exerting a force on the earth. Now you might wonder, how can that be? I'm so small, the earth is so big, right? Well, the fact is, imagine now that instead of being a small human relative to a big earth, you were 2 planets, same size. One planet would pull on the other, and the other would pull on the one. Same concept. You both exert a force on one another. So the guy here, the picture, is attracted by the earth, but he is also attracting the earth. So that's the action-reaction of gravity itself, right? And so if this guy now is a few feet above the ground, Earth will accelerate the guy down, and the guy will accelerate Earth up. Now, you might wonder, this makes no sense. I move, not the Earth. Well, yes, it turns out that the Earth is also moving. And what really happens is that the Earth is moving very little relative to you, or to what we would call the center of mass of you and Earth. Because the Earth is so heavy, so large, so massive, its motion in space will be very small relative to your motion. So in practice, there's this thing that we call the center of mass between you and the Earth. And as you fall towards the Earth will fall towards you. In practice, what that means is you fall towards the center of mass, the Earth falls towards the center of mass as well, but the Earth being so much larger, its motion relative to the center of mass frame is very small. Something that we will revisit again later in this class. For the time being, all you need to understand is that Earth is pulling on you and you are pulling on Earth. As you are at some elevation relative to the ground. Now, when you reach the ground, then there's an additional phenomenon that takes place. You're still being pulled by Earth, but now there's a surface of the ground. And so the surface of the ground is resisting you falling further. And so the ground of the Earth, the surface, the dirt, whatever the material is, this material is pushing you up. And it's pushing you up with a force such that the net force on your body is zero. Gravity down, the push of the ground on you cancel. Right? Now, this is not action equals reaction. These are really distinct forces. They are related because the pull is causing the force of Earth, the ground, on you. The action and reaction is the Earth is pushing you up, and your feet are standing on the ground, and they're pushing the ground down. I remember one of these movies where journey to the center of the Earth, and as they come down to the volcano, they find themselves on something that looks like a piece of ice, and then they say, "Hey, don't move! The ice is cracking." So what's going on? The Earth is pulling on the guys. The ice is resisting that motion by providing an upward force on the guys, and the guys are pushing on the ice, and eventually the ice is unable to sustain their weight, so the ice breaks and they keep falling down the volcano shaft. Here's another illustration of Newton's third law. So imagine that we have a small cart. Focus on the image in A here, panel A. And fitted with this cart is a spring-loaded mechanism with a plunger, right? Where the tip here, the black tip, is the visible part of the plunger, and inside you have a spring-loaded mechanism. So you push in the plunger, and when you release it, the plunger comes out like so. So now take this contraption and butt it against the wall, as in panel B, and now the contraption is the spring-loaded plunger is pushed in, and now release it. Well, as you release it, the cart pushes onto the plunger for the plunger to get out. But now there's a wall anchored to the ground, and so the plunger imparts a force onto the wall, but given that the wall is itself anchored into the ground, it will not move, but it will react, action equal reaction, onto the cart. And so the fact of pushing the plunger out, thereby producing a force onto the wall, will make the wall react with an equal force, an equal magnitude force, directed towards the right, and this force then will accelerate the cart. And the cart then will bounce off the wall at some finite speed. It will be accelerated for the duration of the contact between the plunger and the wall, and then as the contact stops, the force acting from the wall onto the cart, that force will stop and the cart will just roll away at constant speed. If there's friction in the system, then eventually the cart will slow down and stop. But the important point is that during the extension of the plunger, there will be a force of the wall onto the cart as there is a force of the plunger onto the wall. Action equal reaction. Same thing can be done if you now replace the wall by another cart. So now we have two carts with equal mass. One carries the plunger, the other doesn't. And so as the plunger expands out, it will exert a force on the cart on the left, but the cart on the left is opposing a change of its motion. It has inertia, and as such, it will react with a force on the cart on the right. And so you have a force on the cart on the left due to the cart on the right with its plunger, and the cart on the left reacts to that force by creating its own force onto the cart on the right. As a result of this, both carts will accelerate, one towards the left, one towards the right. And the acceleration of the two carts will be the same so long as they have exactly the same mass. Now we can change the parameters of this problem a little bit by changing the mass of the two carts. So indeed, what if one cart is more massive than the other? And the plunger comes from the other cart. So you have different possibilities here. I'll ask you to think about it for a moment. So I have one small cart which carries the plunger and one larger cart that doesn't. What will happen? Will their acceleration be the same? Will one acceleration be larger, and so on and so forth? What will happen? I will let you think about it. What if one cart is more massive indeed? Well, what if now you have replaced the cart by a rocket or a jet aircraft? Right? So here we have the space shuttle. Well, one of the space shuttle. I'm not sure which one it is actually. And this space shuttle was equipped with a booster piece, right? And at takeoff, both the engine of the shuttle itself and the engine of the booster would be used to create thrust. How does that mean? Well, the fuel in the tank of the booster and the shuttle are used to have a combustion. This combustion produces a gas at very high pressure, and this gas then is expelled through the nozzle of the engine. As such, the gas is now moving at extremely high velocity. So the gas goes from being at rest to being accelerated at very high velocity. And so it is expelled out. So the gas is subjected to an action by the explosion of the gas, by its internal combustion and explosion. In turn, the gas is resisting acceleration. The gas, even though it's a gas, it carries inertia. And so it resists acceleration, which means that it will produce an equal reaction onto the rocket. It will resist acceleration by pushing on the rocket, but pushing in the other direction, which means that the rocket will lift. And that's how rockets can take off. You need to expel the gas at very high velocity. You need to expel a lot of gas really quickly so that now this action produces an equal reaction that propels the rocket upward. Let's take a little detour and talk about distance travel with and without acceleration. If an object has a non-zero velocity, v larger than 0, but no acceleration, that is a equals 0, the distance traveled by the object in the time t is given by d equals vt, right? Constant velocity, constant speed, because there is no acceleration. Now, if the velocity of the object is initially 0, but it has a non-zero acceleration, so v equals 0 at first, but a greater than 0, then the speed of the object will increase. So v equals at. And the distance traveled will be d equal 1/2 at squared. We've done this reasoning already in week 1. In general, however, if you start with a non-zero initial speed or velocity, the distance will depend on the initial velocity as well as the acceleration. And one finds this equation here. And so the distance traveled with and without acceleration will be given by this expression. And so a car is traveling, let's do an exercise. A car is traveling at 15 meters per second. It hits the brakes for 5 seconds with an acceleration of -1 meter per square second. -1. It means that the acceleration is in the direction opposite the velocity. So what is the distance traveling during these 5 seconds? I'll give you a few seconds to think about this, and then we solve. So the distance is equal to v times t plus 1/2 at squared. So v here is the initial velocity, 15. The time is 5 seconds. The acceleration is -1. So we have 1/2 times -1 times 5 squared. And so that becomes 75 minus 12.5, and that is 62.5 meters. So the car is traveling, it will continue to travel in the same direction, but eventually it will come to a stop. But in so doing, it will have covered a distance of 62.5 meters. This reasoning was done in the horizontal direction. Now we can do similar reasoning in the vertical direction, and that enters what we call projectile motion. So now consider this. You have a baseball player, let's say, and this fellow is throwing a ball of his hand vertically at some velocity v. What happens? Well, you know what happens. As the ball goes up, it slows down. Eventually, it reaches a maximum height, and then eventually it comes back down. As it reaches its maximum height, it has zero speed. As it comes down, it accelerates. Its speed is directed towards the ground. Its speed is directed in the same direction as g. As it happens, as the ball is going up, it slows down. Yes, it slows down because of g. G, the gravitational acceleration. The gravitational acceleration is directed always towards the ground. It's the pull of gravity that causes it. And so the speed v is progressively decreasing as the ball goes up. And eventually, as it reaches the apex of its trajectory, it reaches v equals 0. Gravity, the acceleration of gravity is still in the same direction, so the ball will then come down. It will accelerate from v equals 0 to some higher velocity as it comes back down. Now, if you could neglect the air, you will find that when it reaches the hand of the baseball player, the ball will have exactly the same velocity, the same speed as it had when it left the hand of the player. So let's do this quantitatively. Say the ball is thrown up at 20 meters per second. We can ask ourselves how long before it reaches its highest point. So the acceleration is delta v over delta t. Delta v is going to be 0 minus 20. 20 being the original velocity, 0 being the final velocity. 0 minus 20 is minus 20. And it will accomplish this in some time t that we don't know yet. That's what we're trying to figure out. The acceleration is something that we know. We know it is minus 9.8 meters per square second. Minus because it's directed towards the ground. And so we can now solve for t. Minus 20 over minus 9.8. And that is essentially 2 seconds, 2.04 seconds. And during this amount of time, the ball will have gone up by some amount, by some distance. This distance will be d equal to vt plus 1/2 at squared. V is 20 initially, t is 2.04 seconds, 1/2 gives me the minus the 0.5. A is minus, which is why I have a minus here, 9.8, and then t squared is 2.04 to the power 2. You compute this, you get 20.39 meters. So the ball will go up by 20 meters, which amounts to approximately 60 feet before it comes to a stop and accelerates backward towards the ground. The distance traveled down is equal to the distance traveled up, right? Going distance down is minus the distance up. And so, but on the way down, you start from rest. And so the distance down is 1/2 at squared. A is minus 9.8. The minus cancel, and I can now solve. And so t equals the square root of minus 2d over a, and that's indeed 2.04 seconds. In other words, it takes the same amount of time to go down as it took to go up. And it also means that it will reach the same speed at the bottom that it had starting with before it went up. So think about this in a specific example. A ball is thrown straight up at 9.8 meters per second, a speed of 9.8 meters per second, numerically equal to the acceleration of gravity, 9.8 meters per square second. How long will it take to come back down to the height from where it was launched? How do you do this? Well, the simplest thing is to calculate how long it will go up and essentially multiply by 2. So I'll let you do this. I'll give you a few seconds to do this. Time to go up. Well, it's a change in velocity. 0 at the top minus the initial velocity. And this is going to be equal to the acceleration times t. The acceleration is minus g, right? Minus 9.8. So the t is v over g in numerically. And so that's, that should be, there's a typo here. I really apologize. This should be 9.8 meter per second over 9.8 meter per square second. Again, apologies for the typo. The ratio here is 9.8 over 9.8, which is numerically equal to 1. And so I will try to correct that in a moment. How far or how high does the ball go? Well, you apply the same logic we've applied before, and this is shown here. I'll give you the answer straight away. Now, we can make this a little more interesting. So far, we've assumed that the ball is going straight up, straight down. Now we could, if we play baseball, we're not just moving up and down, we're actually also on a baseball field, so we can throw the ball in some direction. And so that means that the ball in general, balls that we throw, will have this kind of motion. They will go up, reach some maximum height. The velocity along the vertical axis will be 0, but the velocity along the horizontal axis will remain finite. It will remain the same. And then the ball will come down. The horizontal component of the velocity will remain the same, but the vertical component will become larger and larger, pointing down. You can think of this as playing baseball or as juggling ball, as illustrated here. Same idea, same principles. Then you can ask yourself, okay, if I'm playing baseball and I'm out in the field and I want to reach the plate, because I want to, get this guy out. He just batted and it was a nice hit, but I managed to catch it, and now I want to retire. The guy was going down by the plate. I need to throw to the plate. So what should be the angle that would maximize the chance of reaching the plate? So what would be the angle that I need to pitch the ball at to throw the farthest away? And the answer is 45 degrees. And to derive this requires calculus, but I'll just here give you the answer, 45 degrees. So 0, 90, and 45 degrees, straight in the middle. Neglecting air, of course. Now, in general, when we move things, when we throw things, when we do things in human space, we are not in 1 dimension, 2 dimension, but we are in 3 dimension, right? X, Y, Z, as illustrated here. So when you have motion along 3 axes, 3 perpendicular axes, we can decompose this motion along each of the 3 axes. And so long as the 3 axes are perpendicular to one another, this decomposition is simple and easy to visualize. If you were to choose the axes to be not perpendicular to one another, but slightly in part parallel to one another, or at least, then you could still do the science, you could still do the physics, you could still do the math. It would just be a little more complicated. So keep it simple by having all 3 axes, X, Y, Z, strictly perpendicular to one another. I remind you of the Pythagorean theorem. If you have a vector with a component in X, a component in Y, and a component in Z, the size of this vector will be the square root of the square of the components along X, Y, and Z. So now we can consider motion in 3D. Now, in general, when you throw a ball, unless there's a lot of wind, the ball will go in whatever direction you threw it at. And so effectively, the motion reduces to 2-dimensional motion. You're in space, you're in 3 dimension, but you're throwing in one direction. So effectively, you will have one parabola, and one parabola is essentially motion in 2D. So Let's imagine that the ball is thrown up with a vertical speed of 10 meters per second, a horizontal speed of 10 meters per second. So you'll note here V sub V, V stands for vertical, V sub H, H stands for horizontal. So you can ask, what is the velocity at the top of the parabola? I'm going to let you think about this for a second. What is the total velocity of the object, the ball, as it reaches the top of its trajectory? Let me give you the answer. 10 meters per second. Why? Well, the component along the y-axis, the component along the vertical axis, of course, goes to 0. At the top of its trajectory, the ball is no longer going upward, and it's not going downward yet. Eventually it will, but not yet. And so it means that at that point, the ball is strictly in a horizontal motion. And because there is no force applied horizontally in this problem, there is no acceleration or deceleration. So the motion of the ball, the speed of the ball along the horizontal axis remains 10 meters per second all throughout this parabolic motion. So as it reaches its maximum height, the ball is at 10 meters per second horizontally. Now you can ask, what is the horizontal velocity when the ball comes back down to the same height from which it was launched? What is the horizontal component? Well, it hasn't changed. It's still 10 meters per second because along the horizontal direction, there is, in fact, no acceleration. The acceleration of the ball is only along the vertical axis. So throughout, the ball goes at 10 meters per second in the horizontal direction. But in the vertical direction, it first goes up, stops, and then comes back down. Then you can ask yourself, what is the total velocity when the ball comes back down to the same height from which it was launched? What is now the total velocity? Right? That means including both the horizontal and vertical component. I'll let you think about it for a few seconds. Well, we saw that the ball started at 10 meters per second up, went in 10 meters per second horizontally. When it reaches the apex of its trajectory, only the horizontal component persists. But when it comes back down, the vertical component is reversed and it accelerates from 0 to the maximum speed. And the maximum speed at equal height will be 10 meters per second pointing down. So as the ball comes back to the same height as it was launched, it has a horizontal component of 10 meters per second and a vertical component pointing down of 10 meters per second as well. So that's 10 squared plus 10 squared. Take the square root of that. That's square root of 2 times 10. Then you can ask, what if the force is not constant? So far, we've discussed cases where the acceleration was considered to be fixed, constant, 0 or some fixed value. We've discussed several examples where the acceleration is provided by the pull of gravity, the so-called gravitational acceleration, g, which is 9.8 meters per square second near the surface of the Earth. What if the acceleration is not constant? What can be done? Well, in general, it makes the solution of the problems a little more complicated. One needs to use calculus to do the integration of the equations of motion. And calculus is not required in this class, so we're not going to discuss this all that much, but it can be done. And I will just give you a couple examples of this. So one example is known as the motion of a spring, and a mass connected to a spring is illustrated here. So let's say you have a spring attached to the ceiling of a room, and to the spring you attach a mass, illustrated in red. And so as you attach the mass, the spring will become elongated by a little bit, and then you can give it a little kick. So you've played with springs, I'm sure, slinkies maybe, when you were young. And so as you kick the spring and the mass, the spring will oscillate and the mass will go up and down, and it will persist in this motion for a while. Eventually it will stop because of friction, but if there was no friction, it would just go up and down like this for a long time. When you analyze this problem in detail, you find that there's a force acting on the ball exerted by the spring. And this force, due to the spring onto the ball, causes the acceleration of the ball. What one finds is that the acceleration is inversely proportional to the distance from what we call the equilibrium. So we start from equilibrium here, this position, and as you bring the spring down, gravity is pulling on the ball, but the spring is pulling up on the ball. And it turns out that this force of the spring onto the ball is some constant K times the distance of stretch of the spring, the distance by which one has stretched the spring. There's a minus, which is here to tell us that it's a restoring force. So if you stretch X this way, the force due to the spring will be the other way. This diagram is actually not quite accurate. The force shown is the pull of gravity. Or it's the force where the mass would become in equilibrium due to gravity. Anyhow, what's going on is that the force due to the spring would tend to restore, or to try to pull the mass upward when X is below the equilibration line. Now, of course, as the spring pulls up on the object, on the ball will go up. It won't stop, and it will go past its position of equilibrium. And now X will be on the other side, and now the spring will be compressed, and the force now will be in the other direction. So that's why there's a minus here. And so what this looks like in practice, so what this looks like in practice is now I can draw the position along the x-axis, or the distance to the line of equilibrium. And what we find is that it has this particular shape. And this particular shape, so this is the distance as a function of time. And so that's the position of the ball relative to the line of equilibrium here. And so you see that the ball will go down, and so the ball starts from some position, it goes down, the spring pulls it back up, it accelerates, and then it slows down, and it stops, and then it goes back down, and so on. And this motion repeats as long as friction doesn't stop it. So the top graph in green shows the position, or the distance to the line of equilibrium. The bottom line in blue shows the speed, the vertical speed of the object. And so as the object is here at the top, it has zero velocity. You let it go, the object is pulled by gravity, so it will stretch the spring, and so the object accelerates down, at which point the spring is pulling it back up with a force equal to the force of gravity, so the net force becomes zero, and now it starts to accelerate back up. And then it will reach a maximum point and it will eventually oscillate like this. So you see that the motion is up, down, whereas the velocity is zero, down, zero. So what you see is the maximum of position corresponds to zero velocity. The minimum of position corresponds to also zero velocity. And the position, the ball being at equilibrium here means that the ball is going maximum speed downward or maximum speed upward. Like here, the ball is at zero in x, but it has a maximum velocity here. So this is known as simple harmonic motion. It's a periodic motion. It repeats with a fixed period. And it would repeat like this forever if there is no friction. The time period and the frequency can be calculated using calculus. And what one finds is that the frequency of this motion is 1/2 pi times the square root of k, being this constant associated with the spring, the so-called spring constant, divided by the mass of the ball. This neglects, evidently, the mass of the spring itself. If you want to account for the mass of the spring, it becomes a little more complicated. But this is good enough in general. And this is a technique that was used by astronauts on the space station to measure their weight. If you live in zero gravity because you're in free fall around the Earth, you don't need to use your muscle, right? There's not as large a need for the use of muscle, so the muscles tend to atrophy, and then the person will progressively lose mass. Astronauts try to have a pretty strong regimen of exercise. They try to do all kinds of lifting and pulling and running as they live on a space station. But even so, they tend to lose weight. And so when astronauts were still first put in orbit, it wasn't clear how fast they would lose this weight, and so engineers designed this mechanism here to measure their weight. Since they are in free fall, you cannot use a scale in the way that we use on Earth, and so they designed this mechanism based on the frequency of this motion under a spring, the action of a spring of known force, of known spring constant K. And they found that the astronauts are in fact losing weight pretty fast. And in fact, they found that after 2 months in space, an astronaut would typically have this oscillation go 10% faster, which means that their mass has decreased by 18% in that short amount of time. So if you have a weight problem, maybe you should consider going in space. No, that's not a good idea. Okay. Yet another example is Newton's law of gravitation, or universal gravitation. So far, we have spoken about the acceleration of gravity near the surface, but in general, the connection between the force and the objects is a slightly more complicated. So Earth exerts a force on us and all objects near its surface, but it also exerts a force on distant objects such as the moon or other planets. And it was in fact, one of the greatest discovery of Newton to realize that what's happening near the surface of the Earth is the same thing that happens between the planets. It's the same type of force. It's gravity exerted at short or long distance, and it's the same force. It's the same action by gravity that compels the stuff to fall to the ground or the planets to be in orbit around one another, or planets being in orbit around the sun, as I should say. So the same type of force. And so Newton eventually had to figure out, how does this gravitational force works? How is it acting on objects? And he looked at the moon, and he eventually was able to figure it out. And then eventually he also looked at the motion of planets such as Mars, and he came up with the same conclusion. So the universal gravitation is also a force that obeys action equals reaction. It states that if you have a planet pulling on another planet, then this other planet is also pulling on the first planet. So if you have one planet here pulling on this one, you'll have a certain force between the two. So the big one is pulling on the small one is pulling on the big one. Now, if I change the size of the small one, the force, if I double the size of the small one, the force will be multiplied by 2 both ways. Newton also figured out that the size of the force between the two bodies depends on the distance between them, and effectively the square of the distance. And so, for example, the sun is much more massive than Earth, but its force on us, humans, is much less because the sun is very far from us and the Earth is very close. So we don't feel, quote unquote, the force due to the sun, but the sun nonetheless expresses or exerts a force on us. So does the moon. The moon exerts a force on all things, but this force is substantially smaller than the force due to Earth. That said, the moon and the Earth, the moon and the sun exert a force on the water at the surface of the Earth, and this force is what causes the tides. Anyhow, Newton needed proof to do all of this, and he examines the shape and the speed of moon's orbit, and he figured out that the relation between the distance and the masses is given by this expression here. So the force of gravity between two objects, the big one on the small one and the small one on the big one, it's the same magnitude of force. The direction is reversed, and the magnitude is some constant, so-called universal gravitational constant, or sometimes we call it big G. And the mass of one of the planet, the mass of the other planet, and divided by the square of the distance that separates them. The distance being measured from center to center. And this is where we will stop. One can do calculations with this, and maybe we'll get to that, but in some other time, not at this point. So thank you for your attention, and I will see you in week 3.